Okay, so an amine question, and more specifically, the relative base strength of amines. So let's have a look. We have got E, F, and G, all are weak bases. In E, the NH2 is bonded directly to the benzene ring. On F, we've got the NH2, which is on the end of a chain, which is attached to it. And so we are potentially considering the inductive effect. And in G, we've got the inductive effect again, but we've got the N also bonded directly to the ring. So let's have a look. Let's go through. On E, the lone pair on the N actually becomes an extension of the delocalized ring. The stability is conferred onto it. And what that means is it becomes a lot more stable, it becomes a lot less likely to donate that electron pair. So what we find is that it's less available to accept an H+. So we're thinking that that makes it a weaker base. If we move on, F and G both have the positive inductive effect, whereby the electrons within the CH2CH3 or the CH2CH2 are drawn towards the lone pair on the N, making it more electron releasing, so therefore making it a slightly stronger base. So if the strength of the base is based on the ability to donate a lone pair on the N, we can then put these into the rank order. So the lone pair is most available in F, most available because the N with the lone pair is far away from the benzene ring, but also it has the inductive effect from the CH2NH2. And we know that NH2 is going to be the weakest base because the lone pair becomes an extension of the delocalized ring. So that's going to be the weakest. G is actually influenced by both of those factors. You can look at the lone pair being taken on as part of the delocalized ring, but also there's the inductive effect from the CH2CH3. So that one goes in the middle. And then, final part, amine F can be prepared in a 3-step synthesis starting from methylbenzene. Suggest the structures of the 2 intermediate compounds, and it's important to note here that the equations and mechanisms are not required. They can add to the confusion, they can certainly take up a huge amount of time, so I would not get bogged down in it. Now, I have got my methylbenzene drawn out so I can see what I'm starting with, and I know that I am aiming to make F, which I've also transferred onto this page so you can see it. That was provided earlier within the question. Now, the first thing that you need to consider here is that there must be an extension of the carbon chain. So that is hopefully making you see that we are at some point going to have to use a nitrile group. Now, my product of step 1 is going to be a haloalkane. I need to make the haloalkane so that I can make my nitrile. The haloalkane is basically a free radical substitution mechanism. You don't need to name that here, but hopefully you're recognizing that. And if you do remember that, that will help you to remember the conditions. And that's going to be the addition of chlorine, but in the presence of UV light. And that's what's going to take us to our product in step 1, the C6H5 CH2Cl. Step 2, we're going to add KCN. Don't fall into the trap of adding CN-. The CN- would be the nucleophile. But you can't get CN- on its own. We need the reagent, so it could be KCN, it could be NaCN. And the condition here is really important as well. It needs to be ethanolic and aqueous. You need both of those terms to get that mark. Step 3, For hydrogenation to go from the nitrile to an amine, we need to hydrogenate. And the easiest way to do that is to add hydrogen directly, and when we hydrogenate, we use a nickel catalyst.